So if you haven't yet added the repo to your Google Earth Engine account, there's a link here to get that repo added, the repo story, into your Google Earth Engine account. If you don't see it under your scripts, you can just press the refresh button that should appear there. Also, it's always good practice if you are practicing at home or exploring the chapter by yourself and you run into an error or doesn't know why we're using a certain function, we highly encourage you to use the docs tab of the code editor, check users guides and tutorials provided by the Earth Engine team, and also check Stack Exchange. A lot of people ask the same questions that you have, and there are already responses there for you to how to solve that problem you have. So the first section will be creating this confusion matrix and calculating the accuracies and the metrics that we have just seen. The steps will be as follows. So we'll first import the reference data from chapter F2.1. So if you have not looked at this chapter or missed our walkthrough last week, we built some reference data for image classification in Milan. So we classified the Landsat image that was over Milan in Italy. And these are points. We will use some of those points. So I think we had 25 points per class, and you can see the classes that we have used here on the right. And this reference data, I incorporated 75 more points for each class. So in total, we have 400 points that we looked into the imagery and assigned manually to each class. So 400 points that we use for this chapter F2.2. We then split the data into training and testing. So last week we just took that reference data and then trained a random forest classifier on that and then classified the image. This time we'll take the reference data and split into training and testing. So we'll train the model with this training set, which is a subset of the total reference data points, and then use the testing set to actually classify. So we'll classify the points in this chapter, we will not classify an image. And then we use the random column function in Earth Engine to randomly pick from the reference data points for the training set and the testing set. And we will divide it using this 80-20 proportion. So 80% for training, 20% for testing. Then we'll train the classifier with the training data and then test the classification with the testing data. Then to get the confusion matrix and the accuracies, we will use this error matrix function, and then also additional functions that will get the specific metrics. So here's just, memorize this, because when we will be looking to the error matrix, the order that we'll see the pixels, the pixel numbers there, how many pixels were correctly classified as forest, developed, etc., will be in this order. So forests first, developed, water, and then finally herbaceous. And then this would be, as I said, we'll get this output that we're seeing here, and you can see there are no labels, but you can see that this is a confusion matrix. So, but this one has 4 rows and 4 columns because we're dealing with 4 classes. The one we just showed in the theory part of this presentation was just a 2x2, right? So here, for example, is that diagonal of those correctly classified pixels, and you can see, for example, here this 2 here means that if you remember, the predicted classes are here in the rows, and then actual classes are the columns. So 2 pixels here were predicted as developed because it's the second class that we have. But they were actually herbaceous because it's the last one here, looking at the column. And then we get overall accuracy, producer's accuracy for each class, consumer's accuracy for each class, and then the kappa coefficient. So I'll just exit here the presentation, and I have here the code editor open. So you can go ahead, open the code editor. I'm gonna increase here a little bit the zoom so you can see this better. And then here in the book repository, part F of fundamentals, F2, interpreting images, you have F2.2, accuracy assessment. And then we'll work with the first checkpoint. So 22.8, F2.2.8. And as I like to do, I'll just open a new code editor because I'll be copying and pasting bits of the code to explain step by step. So while this new blank script loads, what I'll do, I'll just copy here from lines 1 through 16. And I'll paste here my blank script. So as we saw on the slide, the first thing we do here is import the reference data set. And this is from chapter F2.1 plus additional points that we have created for chapter F2.2. So this is, just calling this feature collection, which are our set of points. And if I do here print data, which is the variable name here that I defined for the reference points, you see that we'll have 400 elements or 400 points within this feature collection. And if I open here the list of features, we have points with 11 properties. And if you recall, if I open here properties of the first point, these are the spectral information at that point location from the image that we chose to classify. We have the class, so this point is a forest pixel. And I also added spectral indices as well. So we have NDVI and NDWI values here for each of the points that we have collected. Close this. And then since we'll be doing a new classification with just part of these points, so 80% of these points will be used for training, 20% for classification to assess if it's good or not. These are the prediction bands. So instead of just using spectral bands, last week a lot of people asked, what about spectral indices? Should we use that? Does that improve the classification or not? Here I added the two spectral indices, NDVI and NDWI, so vegetation and water indices. And also we have a thermal band as well. So we have spectral here, we have a thermal one, so ST band 10. So for example, we have a class that is developed, right? And a lot of the pixels, a lot of the urban features we have in the region, in the image are, for example, buildings or asphalt, and usually those objects have higher temperatures than, for example, the herbaceous class that we have in this example. So we can use the thermal information as well to fit into the model, so it learns how to separate better the classes with not just using spectral information, but thermal information as well. So I'll just use the sprints to show you what the feature collection looks like. I'll go back and copy lines 18 through 23. I'll paste here. So what we're doing here, as I said, we use this random column function here. So I'm creating a new variable called training testing. And then this will be my data variable, which is my points here, the reference data points. And I'm adding this random column function. So I'll just quickly comment this out. And I'll print again this training testing, so just so you see what the random column function does. If we search here in the docs and search for random column, we can see that we have the function for both feature collection and image collection as well. So we'll check the one for feature collection, which is the one we are using, but it's pretty much, it should be pretty much the same function. And what it does, it creates a column, so it would be like a new property in the attribute table of our reference data that contains pseudo-random numbers. The default option here is that the values, the random values that are assigned to this property called random, distribution is uniform. So we have values ranging from 0 to 1. And since it's a uniform distribution, the mean value of our set will be 0, and then standard deviation is 1. So we have random values assigned to each of these points that are from 0 to 1, and since it's a uniform distribution, it's pretty much having the proportions that we want to divide. So if we say I want to 80% from my training set, we'll pretty much get roughly 80% of the points for the training set, and then 20% for the testing set. So here, for example, if I open this first point here and look into the properties, we can now see it has 12 properties. We can see that this random column here, this random property was created, and it has this value of 0.9688 something, right? And then if I open one down here at the bottom, just to compare the second to last one, it's a value really close to 0, right? It's 0.1812 something. So values here in between will have 0.5 something. So it's a uniform distribution. And then if I uncomment these two lines here, I'll erase the sprint call. I have a new variable training set, which will be the training testing variable, and I'm filtering it to have, I want points that have less than 0.8 value for the random column. So this means I'm taking 80% of my points for the training set. And I do the same for testing set, but instead of using less than, I use greater than or equal to 0.8. So this assures that I get the remaining 20% roughly of my reference data for just the testing set. So if I quickly do here, print training set dot size, this will give me how many points I have in this new filtered feature collection, and I do the same for the testing. So from 400, we have 317 points for training, 83 for testing. If someone is really good at math, you can see that it's roughly 80% here and 20% here. Okay. I'll erase these print calls and I'll go back here. Now I'll copy lines 25 through 30. I'll paste here. So now we're training a random forest classifier. We use random forest just because we used that in the last chapter as well, besides the cart classifier. So we have EE.classifier, it's my random forest. We have 50 trees, decision trees defined for this random forest classifier. We're going to train that by using just the training set, so just the 80% of the reference data we have. Again, if you recall, you need to define the class property, so which property in our points have the class information. So this is labeled as class in our case. And then input properties are what we are using to train the model. So this is the spectral information, the thermal information. So it's the prediction bands that we have. So this is training our random forest classifier. And then now to test the classification, we'll copy here lines 32 through 38. We paste here. We have here the trained random forest classifier, and then now we do the classification on the testing set. So that way, our model haven't seen these points before. So we use that then to assess the classification. And then after this, after we classify the points, we're classifying the points, we have the error matrix function, which is the function used to generate that confusion matrix or error matrix. And then we have to say which of the properties in our points are the actual, contains the actual information, so that the information that is reality in our case is class, because that's the one we collected. And then the predicted argument here, so the values that were predicted by the model, is labeled as classification. If you recall, last week, once we applied this classify function into the image, that image contained a band which was labeled classification. This is the same case for the points here. You will just add a new property that feature collection. So for each point, we'll have a new property called classification that will contain the number of the class that the model classified that point into. So here, classification, and then we're generating the error matrix here. Then finally, we copy here the rest of the script, which is where we're actually going to print the results that we have. So first is the confusion matrix. So if I did here print confusion matrix, it's exactly what I have here, confusion matrix. We would see just that confusion matrix there. Then within this error matrix function, we can also call additional ones. So we have accuracy. This one would be the overall accuracy. We have producer's accuracy. We have consumer's accuracy, which is the user's accuracy as well. And then we also have the kappa coefficient. So these are all as functions in Earth Engine, which is really nice for us because we don't need to do those calculations. So those formulas that we saw, everything is already as an embedded function in Earth Engine. So if I run this, we'll get the results here on the console. Take a second to. And then here we have first the confusion matrix. And we can see here a few pixels were wrongly classified. So the ones that are outside of the diagonal are the ones wrongly classified. We have overall accuracy, which is 87.95, which is fairly good, pretty good, this classification. We have producer's accuracy. So here from the classified pixels as forest, 100% of them were correctly classified. So we have 1, so it's 100%. So our model really classifies forest pixels well because it's 100. For developer, we have 88.88%. For water, 87.5, and then herbaceous 77.2.3. And then we have consumer's accuracy as well, which would be user's accuracy. From if you're looking at the map, here's it's different from producers, right? If you recall the theory part. So these are from the pixels that are actually forest. 90% of them were classified as forest. So we have there 10% that have been missed, that are classified as something else, right? And then Here's the same for developed water. So from all the pixels that are water, we have classified them as water correctly. But here the number is different because we probably classified a pixel that is, I don't know, developed or forest as water. So that's why we have a different accuracy here for the water class. Remember, this is 0 is forest, 1 developed, 2 water, and 3 herbaceous. Then for the kappa coefficient, we have 83.9% of accuracy, so a little bit lower than the overall accuracy. So that's why it's important to have not only overall accuracy, but also these producers and users accuracies, because you can check the accuracy of each class specifically. So you can say, okay, this is roughly 88%, I'm done, my job is done, the map is super good. But if you look, for example, at the herbaceous class, 77 is not as good as, having 80 plus accuracy. So you might think about adding more reference data into the herbaceous class. The same here with developed, we have 76. So probably these two classes are being misclassified. And if you remember from the previous chapter, that's exactly what we observed visually on the map. So when we were looking at the classified image, we saw that a lot of areas that, the mix between urban and herbaceous, urban was being classified as herbaceous and herbaceous as urban. So the model was having difficulties classifying those two classes. So from these results, one can go and define that, okay, we need more reference data for herbaceous and urban. So we focus, getting more training data for those two classes. We don't need, like for forest, for example, it looks pretty good, right? So you can take these type of decisions based on these results.